Okay, I think we can start. I don't see anybody else joining. Feel free to use the emojis in the chat. Can you guys give me a thumbs up if we can start? Okay, we got one, got two. Okay, thank you very much. So regarding the chat, we are recording. Please be aware of that. And if you can, please turn on your camera. I think makes a better experience for everybody. And yeah, let's start with the event. So I want to thank everybody for joining today. As you all know, today we are talking about the OCELOT challenge, and this is the online event connected with MICCAI. And yeah, thank you all the participants to take their time. I know it's we are all very busy and the time zone is very complicated, so it's actually a good turnout. Okay, before jumping into the action of the event, let me tell you a little bit what we're going to do today. We're going to have a short introduction about the challenge itself and the event. Then we're going to have a very short introduction of Lunit and especially what we do in the oncology department, so that we are all on the same page. We understand why this challenge is so important. Then we're going to go through the core of the event, which is the presentation for the participants of the event, showing us how they solve this challenge. We're going to have in total 1 hour. Don't worry, we're going to have a break in between. And this is in total 5 presentation split into 2 sessions. And each one will be 7 minutes plus 3 minutes Q&A. Finally, we're going to announce the winner. This is going to be very short. And then the concluding remarks. Before jumping into the introduction, I would like to thank all the organizers, as you can see them here, and especially the first 3 organizers are the main authors of the paper. And I'm down here. I'm Biagio, if you want to Google me, and if you want to get in contact with me. As I will say at the end of the event, I'm also going to be in MICCAI, so if you have more questions or you want to get in contact and you go to MICCAI, you can contact me. But for now, let's give the word to one of the best engineers we have at Lunit, Aaron, who is going to give us the introduction on the challenge who he actively created. So Aaron, please take over.
Hey, can you hear us?
Yes, we can hear you.
Right. You received the screen? Good. Yeah.
Yes, we see.
Yeah. This is Aaron. Thank you very much, Biagio, for welcoming me. And in particular, I'd like to thank everybody for coming today and for participating. I know it takes a lot of time to set up your code, prepare your approach, and everything for this particularly OCELOT challenge. So I'm very thankful for your time that has participated in this challenge. But I'd like to step back a little bit and check and discuss a little bit more on the problem itself. We've been talking about the cell detection and the tissue segmentation and how these 2 things are related. And to do that, I'd like to walk you through an experience that we had in Lunit. So in many cases, in computational pathology, you have to end up working with these whole slide images. You might be familiar with them already. They are scanned images from very large images, which are scanned from biopsy samples. And usually they're about like 100,000 pixels for each of the sites. So it's massive size. So it is common for pathologists and also AI models to zoom in a little bit more and check different contexts to better understand this massive image. So let's do that. Let's zoom in a little bit more on this particular region with the white area circle in the center. So at the moment, we can maybe see better regions. We can see more areas that are more darker than others, maybe more density on some cells. But it's just still too early to clearly understand what is going on. So it could be good to zoom in a little bit more. So let's take this area with the white circle in the center. Now we might be able to better see the cells, at least we can see them. To me, they look pretty similar, at least. And perhaps this is the good moment to use a segmentation model, for example, to understand which are the regions in this image. So we do that, we take a model, and then the model says that mostly all the area ends up being a cancer area, okay? Now, I'm curious about the cells. I'm gonna look at this particular region. You know that cell models requires a little bit more fine-grained details, and this is what we see in that region. Like, we can see better the morphology, can better understand the context, so we can better predict cells. And this is what we get from our cell model. So they're pretty well localized, and the model says the class is identified as class A, which we denote in green. Okay. Now, I'm a very curious man, so I will check what, I'm just curious about the contiguous grid. Let me check here. But the thing is, here we get different predictions. The cell is still well localized. Maybe there are some that has been missed, but anyway, all the classes without exception are predicted with class B. But to be honest, to me, this is a little bit not optimal maybe, because everything is under cancer area and the cells looks very similar to me. So, okay, let's do one thing. Let's predict the cells in let's do inference on all the cells in this grid. So this is what we get, more or less a even ratio between the class A and class B. There are some predicted cells with class C, but that's not what captures my eye the most. Perhaps you can already notice that there are some lines and some grid-like artifacts. There are some squares, and that's not very desirable. That's maybe, to my eye, even though I'm not a pathologist, that's not optimal. So let's recap here and let's evaluate what went wrong. So first thing that I can come up with is that there are two tasks here. There is a segmentation model that is capturing the areas, cancer area or no cancer area. And then there is some cells predicted, but they are not well communicating. Like, we have two grids that are under cancer area, which are very near to each other, contiguous. And then we have that the predicted cells are completely different. For your reference, class B and class A, one is tumor cells and the other one is immune cells. So it makes not total sense here. Something is going wrong. But something even more noticeable is the grid artifacts. And I attribute this to the narrow field of view that the cell model sees. It's very narrow, and that this leads to this line and this grid artifacts effects. So here we have two problems. We have two tasks that are not communicating, and then at the same time, we have some narrow vision for the cell model. So we wanted to solve this problem, and how we wanted to start by solving this problem is through the data. And that's how we came up by creating the OCELOT data set. Now, the OCELOT data set is composed of paired images. On the left, you have the large field of view image, and overlapping inside in a random location, you have the cell patch, the cell grid, which is annotated for the cells. Now, for the tissue annotations, we annotate cancer areas with a segmentation mask and background. On the cell images, we annotate with point notations the tumor cells and the background cells. Now, if we take a look to the statistics, we found that, well, first of all, the tissue annotations are pretty well balanced. We have like a 40% CA versus a 60% BG. I would say that that's pretty well balanced. But something even more interesting is, where are those cell annotations living in? Is my tumor cell inside at CA or in BG? So we have some intertask here statistics. And what we observe is that tumor cells end up living most likely inside the cancer area, which is intuitive, like tumor cells inside cancer. And we have some marginal cells that lives also in the background area. In the opposite side, we also find that the background cells, which are anything that it's not tumor cell, immune cells, or any type of lymphocyte or anything like that, are living in the background and with some marginal cells inside the CA. This actually extends our opinion, our observations before of the problem that these two tasks should be connected, because there is actually in the data, we find that there is some correlations. We had, we thought that our direction is promising, and so we decided to submit our work to CVPR, and luckily we got accepted. Along with these data set, we also provided some models and compare them with the cell-only baseline. We found that the models that are trained with jointly with two tasks with bigger context outperforms quite a lot the cell-only models, and that's very encouraging. Now, we were curious on we wanted to go one step further and ask the community what are their insights on our data. Maybe they could think that our direction is not the best, or maybe not, but we wanted to see people playing around with our data. So we decided to release the data set and ask for participation in a grand challenge that we had in MICCAI 2023. So I'd like to dig in a little bit more on the second part, on the OCELOT challenge, which is entertaining us today. So the participation was as follows. There were about 290 participants. They were grouped in 41 teams. To me, this sounds like a great number. I'm very happy about these numbers. We have global participation. We have mainly Asia, Europe, Middle East, and North America, especially with high participation from China. On the submission side, we got an exponential curve here. I guess, like human nature, we leave everything for the end of the validation. We have a total of 260 submissions. This is a pretty reasonable number. On the other side, for the test submissions, we get a little bit more, but note that the submissions from the test side are mainly the submissions from the highest ranked validation performance. So it's a fair number. In terms of this presentation already mentioned by Biagio, today we are going to be listening to the presentation of the best 5 performing methods or teams in this challenge. Among them, 3 of them will be awarded economically. But I'd like to just thank you all because I think you did a great job. Yeah, thank you very much. And so till here, we've been talking about the motivation, why this problem came to be and why is this important to Lunit. I also talked about the data set and how it's composed very briefly. And then I talked a little bit more on the challenge that is taking place today, at least the event. So now I'd like to introduce Dr. Seonwook Park, research scientist and team leader of Lunit, who in the oncology AI research, who will be talking a little bit more on Lunit.
Thank you, Aaron. You want to see the chair? That doesn't matter. Okay. All right. Hello, everyone. I hope you can still hear me loud and clear. Thank you, Aaron, and thank you, Biagio, for the initial parts. Today, I have the pleasure to tell you a little bit about Lunit. As you know, the entire OCELOT paper dataset and challenge was a company-led effort, and this company is located in South Korea. Let me tell you a little bit about who we are, what we do, and why we did OCELOT. So firstly, what is Lunit? Lunit is a first-generation medical AI startup. It was founded in 2013, so it's been surprisingly a while. We have over 300 employees now in various locations around the world. And since last year, we are a publicly listed company on the Korean Stock Exchange. In our early days, we ranked pretty well in various AI competitions and challenges and have consistently been gaining some international recognition, for instance, from the World Economic Forum. And we care a lot about publishing our clinical evidence. So we do so at top-tier medical journals, and we publish a lot of papers and abstracts there, and also work with leading hospitals around the world in conducting our research and validation efforts. Lastly, in recent times, we've had some commercial success, and so we have steadily increasing revenues and more partners that have large market shares in their respective medical device businesses. Now, that's a lot of marketing talk and it sounds fine, but what do we actually do? So I think it's worth mentioning our mission, and that mission is to conquer cancer through AI. At Lunit, we strongly believe that AI is the key to understanding and treating cancer. And so at this moment, how do we do this? Well, in the beginnings of Lunit, we found that the world is collecting increasingly many medical images, but existing algorithms have their own weaknesses. And there is an increasing need to assist radiologists such that they can do their work faster. We also saw that cancer treatment methods have varying response rates and are expensive, and therefore it's important and critical to recommend the most appropriate treatment options to patients. And so we addressed these problems in mainly two ways so far. Firstly, it's by accurate and early diagnosis of cancer via modalities such as chest X-ray and mammograms. And secondly, it's by histology image analysis, something that many of you are familiar with. And this is to understand which therapies will work best for the patient. And these two working together would hopefully increase the survival of cancer patients in general. And now my colleagues and I, we work on the Lunit Scope line of products. And that one focuses on assisting cancer treatment with microscope image analysis. So let's talk a tiny bit more about that. Our department's AI research work, it focuses on the initial step of the product's workflow. And in that step, we mostly detect and quantify cells on a whole slide image, or WSI. We specifically aim to detect so-called tumor-infiltrating lymphocytes, and that means lymphocytes or immune cells that are located on cancer area or supporting structures. Based on the density of those TILs, or tumor-infiltrating lymphocytes, on tumor or stroma areas, we can classify subregions of a WSI as being part of one of three immune phenotypes. And that final generated map of different immune phenotypes can then be used to construct an AI-based score. And by simply thresholding the score, we're able to predict whether a patient is likely to respond to immunotherapy. Now, if we do this well, we can save patients time as well as money, and hopefully impact medical insurance companies and how they work as well. But at the basis of all of this is the important task of detecting cells and segmenting regions. So I'm repeating myself a bit, but one of the key tasks that we have is in finding and classifying cells. And so I think you'll remember this visual sample from Aron's talk earlier, about 10 minutes ago. And in Aron's talk, he spoke about the issue of visual artifacts or grid-like artifacts due to the lack of cell tissue communication or field of view. And in addition to this problem, we had another similar issue. Let's take a look at it. So in this image presented to you now, do you believe that there are tumor cells? And if so, which ones of them are tumor cells? And honestly, as an AI researcher who has only ever done computer vision, I have no clue. So I had to ask our in-house pathologist. And so our full-time pathologist, Dr. Tae-Bom Lee, told us that the cells in the middle area are not tumor cells. But based on my years of experience as a computer vision person, looking at pathology images, I thought those cells looked pretty weird. And well, indeed, our Lunit scope cell model agrees. So it feels that the middle cells are probably tumor cells. Now, here's the problem. if we zoom out and we ask the tissue region segmentation model that has a much larger input field of view, it will say that the cancer area is actually kind of far off to the left. And the cells that we were actually looking at before, they're not considered to be on top of cancer area. And that means it's likely that they are not tumor cells. And so as you already know, our OCELOT paper, which was published at CVPR 2023, has the potential to address these many problems. And so indeed, we recently found that when we take Lunit Scope IO, our flagship product, and integrate the OCELOT concept, such that we can do joint cell tissue detection and segmentation, we have many good effects, such as the removal of artifacts and the reduction of mistakes. And let me illustrate this to you. Here is an example that you've seen at least 5 times today. Sorry about that. But you will see that there are visual artifacts that are very prominent. But by adopting OCELOT, they vanish. And so tumor cells are consistently located now on top of cancer area without any confusion that occurs due to limited field of view. Here's a side-by-side, and you can see that the results are really quite striking. Now, we know that we can remove artifacts, or can't say always, but at least mostly. But let's look at mistakes. So we've seen this example before. There are many mistakes being made. Probably it's hard to tell what are the mistakes, so let's see the results after OCELOT. So you can see that immediately the left-hand side cells, they're converted from being not tumor cells to tumor cells. And then the fewer cells on the right-hand side, they used to be misclassified as tumor cells, but are less so. And so again, the difference is quite striking, visually speaking. And so OCELOT as a concept definitely works, and it's already helping us in improving our products. And at Lunit, we very much pride ourselves in striving for top-tier published research, and at the same time as producing cutting-edge products simultaneously. And so you might be wondering, okay, fine, you did your research, you applied it to your product, it works. So why are you releasing the data set and hosting a challenge? It's actually one of the most common questions that we receive. And so we have a few reasons. Firstly, we want to elevate the importance of this approach, this multi-context approach to cell detection. We're not the first, obviously, but we want to emphasize that it's very important to approach in this way. And if many people work on this problem, we would be able to contribute to the cell detection and counting task, which is highly well-established, interpretable, and an essential approach to whole slide image analysis. Secondly, we would like to improve our products further by adopting published solutions, that is, potentially your published works. And lastly, you might have guessed, we would like to encourage you to come and work with us. So let me take a little detour and talk about Lunit's AI division. Now, Lunit's AI division consists of international researchers and engineers. 40% of them are from outside of Korea, which is quite atypical for Korea. And we have many well-cited senior researchers. We continuously organize academic activities, including this particular MICCAI challenge that you are attending the online event for. And we publish at the most top-tier venues consistently in the past 3 years. So we have 7 at CVPR, 3 at MICCAI, and so on. Lastly, we aim always to publish at high-impact medical journals to show and validate our clinical evidence, validate our models and show our clinical evidence. And do consider working with us. Cancer is complex, and we know that complex is what AI does best. And with AI, we can conquer cancer together. So please do check out our careers page and our tech blog. And with this, I'd like to hand it back to Biagio, the host of this session.
Okay, thank you so much. You can just go to the next slide. So thank you so much, Dr. Seonwook, for your very detailed presentation. It was really nice to have an overview of Lunit. Yeah, I guess we are going to start the main event right now, which is going to be the participants' talks. And like I said, we have 5 different teams, and we're going to announce the speaker every time when we can. And the first speaker for the first team is going to be Joshua Millward. I hope I said it right. Joshua, you can please get start sharing the screen and start your talk.
Thank you. Yep, just one moment. You can hear me okay?
I can hear you okay, yes. I can see you. Good, too.
Perfect.
Only need the screen.
There we go.
1 second. Yes, perfect. Thank you. You can start.
Excellent. Thanks very much. So, yeah, hi, everyone. My name is Josh Millward, PhD candidate at Trobe University, Australia, and going to be talking about our submission to the OCELOT Grand Challenge. And on my team, I'm joined by Dr. Jen He and Aidan Nabali. As an overview of our approach to the OCELOT Challenge, where we want to try and find ways we can use tissue information to inform cell detection, we take a 2-stage approach. The first stage is in the form of tissue segmentation, where given the tissue images, we apply a segmentation model to extract a heat map representing where the cancer area is. Following from this, given the cell image, we find and extract the relevant area within the cancer heat map, and then fuse this information together across the channel dimension to a model that ultimately performs cell detection. To go into these models in a little bit more detail, and starting with the tissue segmentation model, so we're using a seg-former model to perform segmentation. One of the key motivators for this is that seg-former is a transformer-based architecture. And one of the nice things about these architectures is the built-in or the inherent self-attention mechanisms, which we feel can make use of more contextual information within the image. When we train this model, we train it to predict across the 3 different classes and using cross-entropy loss to train our model. When we connect this up to our cell detection model, we apply a softmax to the output of the segmentation network and then just extract the cancer area only, which we feed to the cell model. In terms of the image data, we apply Marchenko stain normalization to the tissue images. And during training, we also apply a standard suite of augmentations to the data. When we feed the image data to our model, we do this in 512 by 512 pixel crops, and we resize the data to an effective 0.5 micron per pixel resolution, giving about 256 micrometers of context. Then at inference time, we tile the image data and generate predictions per tile, and then collate the data back together to form the final prediction. Something else that we note is one of the limitations of tiling is that the pixels on the boundary of the tile are missing contextual information that's otherwise present. So to try and mitigate potential negative impacts of this, we firstly run inference on the entire tile, but then we discard predictions made within some boundary of the tile border. And for this model, we choose 64 pixels, meaning that we only retain the inner 384 pixels in this case for that prediction. And these are then is what is used to reconstruct predictions for the entire image. To show some qualitative examples from our segmentation model and for OCELOT as a whole, given the training examples, we split that up into an internal training and validation set so we could track how our models were performing. So this example that you see here comes from one of the models that was just trained on our internal validation set and running inference on the trained on the internal training set, running inference on the internal validation set. So we can see a difference between the ground truth and predictions here, which is quite good concordance between the two. Similarly, here's another example of ground truth and predictions for this model. Finally, when we put all these pieces together and evaluated the qualitative and quantitative results, as you can see on the screen here, we were quite pleased with the performance from the segmentation model. So we thought that it was better to focus more on improving the cell detection model as opposed to continuing to focus on the tissue segmentation model. So that brings us to how does our cell detection model work? For our cell detection model, we're taking at input the cell images and also the heat maps that come from our trained tissue segmentation model run on the corresponding tissue images. These are fused together and passed to another segformer model. And we use this segformer model for detection. And I'll explain how we get segmentation working for detection in the next couple of slides. For this particular model, we're operating at a more zoomed in view as well, 0.2 microns per pixel. So this model is seeing more detail and less context. With this as well, we also train with the same sort of augmentations and also use the output crop margin at inference time. Speaking to how we train this model and how we morph the ground truth into something suitable for segmentation. So the ground truth comes in the form of point annotations on the image. And what we do is per class or per cell type that we're predicting, we generate a heat map, which is 2D Gaussian distributions centered on each ground truth point. And we do this for both classes, which we then stack together, and this becomes the ground truth for our model training. And to train our model, we've used mean squared error loss. Speaking for the predictions, so given an input image, our segmentation model will now output these heat maps per class. And with these heat maps, the next step for us is to take these heat maps and turn them into point detections that we can ultimately use. And the way that we do that is using blob detection within OpenCV. Once we've detected points from these heat maps, we're then able to fuse them back together to the original image and reconstruct all of the cell detections for the entire image. During our model development, as we were trying our different ideas, and particularly on our internal validation set, we did notice there were some cases where we found there was quite poor performance on a particular subset of images in the data set. And upon further inspection of these, we identified that the reason was likely due to under-annotation of the cell images. So we decided to mitigate the potential impact of these on model performance to exclude these from model development and training. And it turned out to be approximately 10% of the training data that we excluded, with varying degrees of what we believe to be under-annotation. Moving towards now some qualitative examples. So here we can see a region unseen to the model during training. We've got a ground truth example and predictions from the model, which has quite high concordance between the two. And likewise, another one here, ground truth and the comparative predicted from the model. Moving on to quantitative evaluation. So this table here is showing results on the ground challenge validation set, where this top row here is from the model that we submitted and ultimately submitted for the ground challenge test set. Given the validation set was released after the leaderboards closed, we were also interested in just inspecting what was the impact of, for example, using the refined data set versus the entire data set to see how much of a difference that actually made. And it was actually quite an interesting finding for us, where we saw that when we trained using the entire data set, there was a noticeable difference in recall on the background cell class, which means that generally the model trained on all of the data was predicting less background cells than the model that was trained on the refined set. So this was an interesting finding for us. In addition, we also inspected the difference between feeding in a single channel or 3-channel heat map from our tissue segmentation model. And we found that there was slightly better performance from doing single channel, which was primarily due to performance in the background cell class. So just to finish up, so a few strengths of our approach. Firstly, our models are trained using different resolutions. So our cell detection model is able to see more of that detailed view at a more zoomed in level, whilst our tissue segmentation model is operating at a more zoomed out view and more context that it can see to make its predictions. Importantly, these models are trained independently. So one of the issues is that there's currently very limited data sets that exist that contain paired cell and tissue annotations. However, with our approach, because we can train these models independently, we can actually leverage data sets that already exist that contain just segmentation annotations or just detection annotations and train them in isolation to utilize more available data to ultimately get more general models. And just finally, I wanted to mention the approach that I've discussed today. This is the one that we found the best performance on the validation set and submitted to the test set. However, there were other approaches that we did try, which we're going to discuss more in our manuscript. So with that said, thanks a lot, everyone, for listening. And yeah, more than happy to open up to any questions.
Great. Really good presentation. Feel free to clap with your emojis. Any questions? I don't see anything in the chat. So if there are any last minute question that you can say, you can raise your hand. I'm not sure where I should see the hands here, but I don't see any hands raised. So I do have a couple of questions, Joshua,
Sure.
if you don't mind.
Yeah.
So I'm really curious to know, you said you removed 10% of the training data, right? Because they were annotated. Do you know the effect that this had on the performance, more or less?
So that's why we tried to evaluate that with the validation set once it was released. So you can see these top two rows, the difference between these, the models were trained in the same way, just either using the refined data set, so 90% of the training set versus 100%. Of course, with these, because when there's more data, there's also a few more iterations during training, but for the most part, things are otherwise the same. And the big difference that we saw was in terms of the background cell class. So there was a notable difference in recall for background cells, which presumably means the model that's trained on all of the data is learning to not predict some background cells for whatever reason that is, whatever pattern it's picking up on. So presumably, and again, not being a pathologist, I can't make a definitive answer on this, but presumably that means that the under-annotation is likely more so happening with background cells than tumor cells, because we saw very similar performance with the tumor cell class.
Yeah, I see. So in summary, it's very important as a data scientist to always check the data beforehand. Yeah, that's a very good accomplishment. Yeah,
I think so. And I think with this as well, it's also can be responsible for model overfitting too. Because the model, if you have these under-annotated examples in your training set, the model can certainly overfit to that, which I think we're seeing to a degree here with worse performance on the validation set for the entire data set. So
okay. Since I don't see any other hands raised, let me ask one last question, then I guess we can move on.
I think so. There is one from Sergio in the chat. I just saw come through.
I don't know where to see that. Sergio? Oh, there it is. Sergio, I think you can ask directly.
Yeah, thank you, Joshua, for your presentation. It was very interesting. I was curious. I noticed that you use Masenko's normalization for the tissue model. Was it only for the tissue model? And if yes, why not for the cell model?
That's an excellent question. It was just for the tissue model. So the initial, during development of our algorithm, the initial plan was to use Marchenko normalization across the board. On further inspection, though, what we found is because when we were computing Marchenko parameters and performing the normalization, we were doing it separately per image. And due to the amount of context in the cell images, sometimes we would get some very bad results from normalization, particularly in some of the cancer types where the color looked very similar across the entire area. So the normalization results were just really wacky for a lot of cases. So we decided that at least for now, it was best to just normalize for the tissue model, but not for the cell model. Ultimately, what we would like to do is, for example, using this in practice, given the whole slide image, you compute the parameters based on the entire whole slide image and apply them to these patches. But it's something that we didn't explore for this challenge, though.
Okay, got it. Thank you for the answer.
No worries.
Okay. Since we have a little bit of time, there is another question from Lydia. She's asking, why did you decide to tile the images? Was it due to memory limitations?
Yeah, look, mostly that's the case, correct. And also by tiling the images, we get consistent sizes into the model. So yeah, look, a bit of both. It also means during training, we can batch things up quite nicely across different examples as well. So yeah.
Okay, thank you again, Joshua. I guess we can move on. So next team is from Zurich, and the speaker is going to be Lydia Schönpflug, if I'm correct. Lydia,
yes,
could you?
Thank you.
There you are. Thank you for sharing the camera, and please get the screen.
Yes. Can you hear me and see my screen?
We can hear you. We can see you. We can see the screen. You can go.
Okay, perfect. Then hello everyone, and thank you so much for this opportunity to present and also for organizing the challenge. My name is Lydia Schönpflug, and I'm part of the Computational and Translational Pathology Lab at the University Hospital and University of Zurich. And together with Professor Dr. Victor Kölzer, we participated in the challenge with our approach that we titled Cell Detection by Soft Instance Segmentation and Consideration of Cell-Tissue Interaction. So let's dive in. One second. Yes, so when we took a look at the data set, as the main task was the cell detection, we decided to first focus on that and to first develop a robust cell detection model and then consider adding the tissue segmentation information once we had that robust model. And when we looked at the ground truth format, as it's the point, and we wanted to approach the task as a segmentation task for the cells, this required a translation from this point annotation into a segmentation map ground truth format. And so we took a look at 3 different approaches to translating that. And the first one we actually took from the Lunit OCELOT paper, where a circle was placed at the cell centroid with a fixed radius of 1.4 micrometers. And then all pixels within that radius were assigned to the cell's class ID. And what you can see visualized here is a ground truth probability map for the tumor cell class. So you either have 0 if, because this is the ground truth, either 0 if it's not part of the tumor cell class, or 1 if it's part of the tumor cell class. And what you can see here is that this leads to well-separable cells. It's a simple approach, and the cells can be detected as the local maxima. But on the other side, this does not take the full cell into account. So here we only reward the model to look at this central region, but we don't encourage it to learn a bigger morphology of the cell. And so to overcome that, we decided to apply a pre-trained model, NuClick, which requires to have the cell-centroid annotation available. And so as we had that, we could produce this full segmentation maps. And so here you can see what that then looks like in the ground truth. And so we trained our model then with full cell pixels. But what you can see now is that the cells can overlap and touch and are not as well separable as before. And also we don't have this local maxima anymore. So this requires then a more sophisticated post-processing where we use morphological operations and watershed. Yeah, but this is a bit trickier to fine-tune. And for this reason, then we were considering how can we combine these first 2 approaches. And as you can see, I titled this the hard segmentation ground truth. And the reason for that is that here we only have these 2 options. Either a pixel fully belongs to background or it fully belongs to the cells class. And so we relaxed this constraint in our next approach where we placed a Gaussian centered at the with the peak at the cell centroid. And then this way we have a more relaxed constraint. And the full cell is still considered, but we also still have this peak at the cell centroid, which allows us to extract the cells as the local maxima. And it also transforms the pixel classification task into regression. So now we use a mean square error loss when before we were using a dice loss. Yeah, so let's take a look then at the results. You can see results here for the mean F1, once on the OCELOT validation, and then also on the test set, which we ran now that it was published. And what you can see is that we see an improvement for the using the hard instance segmentation ground truth on the validation set, but interestingly not on the test set, which might be due to the more tricky post-processing. But then we can see an improvement on both sets for using the soft instance segmentation. And so now that we had this robust baseline for cell detection, we then looked into adding the tissue segmentation. And so we trained the same model, which was also DeepLab V3+ model, with the same architecture, but it's 2 separate models and one for the tissue segmentation. And then we fed its output together with the cell patches input to the cell detection model and retrained. And then in the last step, we added test time augmentation. And so let's take a look of these results as well. And as you can see, interestingly, when we just added the tissue prediction for the validation set, we actually saw a slight decrease in performance. In contrast, on the test set, you can see quite strong improvement. But then when we added the test time augmentation, we could see an improvement for both. And so my assumption was that possibly the model didn't at first, wasn't as robust towards these geometrical variations. And so by adding test time augmentation, we could actually overcome that. Yeah. And so that way we ended up with our final result on the test set of 71.17. Yeah, and that's all from my side. I want to thank you for your attention, and I'm looking forward to any questions.
Thank you so much. Very interesting, a bit more classical approach with Gaussians and stuff.
Yeah.
Do we have any questions? We are pretty good on time. From the audience. Okay, we see Mohammed, you raised your hand. Unmute yourself, okay?
Yeah, hello, and thank you for the presentation. Pretty nice way to tackle the. So I wanted to ask a little bit more about why you thought the tissue segmentation reduced that external validation score of your final model, and was it really the test time augmentation that was the champion, or was it the adding the tissue segmentation?
Yeah, I was wondering about the same thing. And the reason why I thought it would be the test time or the generalization with regards to geometrical variations is that you would assume that if the model is robust towards the geometrical variations, then it wouldn't matter if I turn the picture or if I rotate it or flip it, the model would still have the same prediction, right? This would be ideal. But if by adding the test time augmentation, I can see this improvement, it shows me that the model, in fact, did have some variation with regards to this rotation or flip. And so by adding them, you can see it as an ensemble in some way of, you present the model with all these different rotated or flipped images and then combine the predictions. And so then the ensemble prediction is more robust. So that's why I have this assumption, yeah.
I see, thank you.
You're welcome.
Okay, we have a question from the chat. So they say, I think you mentioned that you used the nucleocentroid in your soft target approach. And I was wondering if it helps because the ground truth cell positions are not consistently located. That is, it's less about hard versus soft, but more about consistent positioning during training.
That's an interesting question. Yeah, I mean, in the end, I don't know even how would you define this perfect centroid location? Because what is the cell's perfect centroid? I think that is very subjective, even maybe from a pathologist perspective. I think what it helps with is that it gives the model a bit more, it encourages it to consider a bigger area as possible, like high peak and highly relevant pixels. But I mean, what was added with the soft instance segmentation is that you actually have more than just this centroid region, right? So where before you only took a look at this 1.4 micrometer radius, now you have even possibly stretched cells, which was the case for more of the background cells. The cells can be quite elongated, and this would not be as considered as much if you just use the centroid, but can help the model to learn that this is a background cell, in fact. So I hope that answered your question a little bit. Yeah.
The answer is makes sense. Thank you for your response.
Welcome.
Okay, I think we can move on. Thank you again, Lydia, for your nice presentation and your solution. The third team is going to be the team from Bio-totem, and the speaker is going to be, sorry for the pronunciation, Shuoyu.
Yeah, Shuoyu. Yeah, Shuoyu.
Okay, we can hear you. Yes.
Okay. Okay, can you see my screen?
1 second. There it is.
Okay, so I'll start. Good afternoon, everyone. So it's our great honor to have the chance here to present our solution for the OCELOT challenge. Our team is from Bio-totem. We are a startup from China, specializing in computational pathology. So I will skip all the backgrounds about the challenge task, is how important nuclear detection and classification is, in the computational pathology tasks. So here is a brief overview of our solution. So compared to the previous two solutions, I think ours is quite simple and probably not as elegant. So basically, we just, in the first stage, we did separately for the tumor area segmentation and for the nuclear detection and classification. So the two models were trained separately, and we just did a very simple post-processing by a weighting and scheme, actually to combine the results of the area segmentation and the nuclear classification results to form the final nuclear detection results. So I will introduce the area segmentation and the nuclear detection classification model separately. So what we did actually for the tumor area segmentation is a model modified from the UPRNet. So UPRNet was originally a multitask framework. It incorporates various visual concepts jointly, but we only adopted the decoder part of it. So which incorporated some of the like FPN or the PPM module actually to be more effective to bring the global prior representations. So what we changed here is the backbone. Actually, we use a VAN, the Visual Attention Network. So the key part of VAN is actually use a very large kernel attention module to enable the self-attention and long-range correlations in self-attention. So although we did not do a very detailed comparative comparisons using this network with other structures, but in our daily work, actually, this combination of VAN with the UPRNet gave us a quite good results in several computational pathology tasks. And also, we're using this model to win the first prize in the previous Tiger Challenge. So we decided to use the exactly same segmentation model in the training strategy here and this task as well. So basically, we allocate the training and validation in the 8:2 ratio to allocate examples, but based on organ. So we can see the overall dice for the training and the validation set. So the green line is for the training, or the yellow one is for the validation. So overall, we can achieve the dice score over 0.9 on the validation set. So we train a model for 40 approaches. So when we calculate the dice on the validation set for each approach and select the highest dice that round the weight using as the final weight for our submission. And we also see the dice on the validation set and for different organs. And we see that actually the segmentation performance is quite stable for all the organs, except for some of the organs like stomach, probably the results are a little bit worse. So we thought about whether we want to train a separate model, segmentation model for each organ type. But unfortunately, we don't have the time to do that. So for the nuclear detection and classification part, actually what we use is a modified version from so-called SFCN OPI network. So since we have the dot annotation of nuclear center as the label, so I think we did it exactly as the first presenter. Actually, we transformed the dot annotation actually to a circle area with the gradient actually for the probability. Actually, at the nuclear center, we have the highest probability to 1. And actually, at the edge of the circle area, actually, we have a 0 probability. So we're using this as the branch truth actually to train the model. So we see that actually has 2 branches here in this network. So the first actually is a detection branch, which is an 80-layer deep FCN network. So the output actually of the detection branch actually will do thresholding. So only those pixels actually with the probability above the threshold from the output of the detection branch. So this is called the objectives prior, actually will be feeding to the second phase for the classification part. So I think the beauty of this is actually when we do the classification of the two different cell types, right? We don't need to incorporate all the pixels from the image. Only those high probability pixels output actually from the detection branch actually will be incorporated in this classification branch. So the training will also, the 3 phases. So the first phase actually will train the detection branch. And in the second phase, we will freeze actually the first several layers and only train actually the classification module 4 part. And in the phase 3, actually, we will unfreeze all the modules and do the joint training together of both detection and the classification. So actually the example allocation to the training and validation is exactly same as we did for the segmentation, but only thing is we exclude 41 images and we manually inspect all these images and found some of them actually for the under annotation. Many of the cells are not annotated. I think this is also reported in the Joshua's presentation as well. So actually we found that after remove these, actually the images, it will give us actually a boost in the cell detection performance. So here we report actually the training and the validation positions, the scores purely from the cell detection and classification network. So we see that we can achieve quite good results from the training data, but actually we see a quite big drop actually from the validation. But this actually is the best score we have. So we select this best nuclear detection model. So the stage 2 actually is a very simple weighting and the combination step. So basically, we want to weight between the output from the cell detection and the area segmentation results. So the idea is that if any class of cell classification probability is high, for example, close to 1, which means the prediction from the cell detection or classification is quite confident, then we may rely on the results from the original cell detection outputs. But if the probability of the two classes actually are quite close, then we incorporate the results more from the segmentation results. So as we can observe, actually when the p-norm actually is the ratio between, for example, we define as the probability of the tumor cells actually divided by the sum of the two classes. So we see that actually when the probability of one class actually is very high, either close to 1 or close to 0, right? Actually, the weight of this actually will be equal to 1. Then actually in the final, the weighting scheme, right? Actually, we will rely mainly on the classification output. Otherwise, we will mainly rely on the segmentation, actually the probability. Actually, we consider another string scenario, which means that the final results will solely rely actually on the segmentation results, which means we allocate all the nuclei detected in the segmented tumor areas as the tumor cells, and all the detected nucleus outside the tumor area as the background nucleus. So it just like give the segmentation results a huge weight. So we call this extreme scenario. So here's the final result. So just using the cell detection model only, so on the validation set, so we achieved the average F1 around 0.9, and actually the performance is quite similar to what we have actually on our the internal validation set. So when we put this adaptive weighting fusing scheme, actually we see a boosting actually for the F1 score, but surprisingly, when we see that we will use the best performance was achieved using extreme weighting, which means the cell detection, the classification results doesn't play a role. If we solely depend on the tissue segmentation results to decide the cell class, actually we have the highest score actually on the validation set. So actually we're actually debating inside of which form actually to submit for the final one. Although we don't think the last one actually purely rely actually on the area segmentation results is a good approach, but we'll still finally submit this solution. So we think this success could be attributed to the biological nature of most cells within tumors being the tumor cells, and most cells in background areas being the background cells. But this might not work for other type of the cells, which don't have this kind of the probability nature. And of course, as other presenters, I think these kind of new innovative approaches, which explore the multitask training and simultaneously using the information from both tissue and cell information, actually could be the better solution. And we're very happy to learn these kind of new solutions here today. Yeah, that's pretty much my presentation today. Thank you.
Thank you. Thank you for your presentation. Okay, we have a question from the chat. Mohammed is asking, did you use manual inspection for removing these 40 and something training samples?
Yeah, actually at the beginning, we didn't notice that. Actually, at the first round, actually, we see some of the images, the score is quite low. So we go back actually to check these images with very, very low score. Then we actually found this situation. So it's a semi-automated manual inspection.
Okay. Joshua, the same question for you, but you can answer in the chat. Any other questions? I see Oncology Lunit has his hand raised.
That would be me.
Okay.
This is Aaron, who presented earlier. I'm wondering, thank you for the presentation, first of all. It was very interesting. I have a question regarding the tissue model. And I see that you have two heads. I'm wondering what is the motivation behind having two heads? And if you try varying having or not having and see what happens.
This is the, frankly speaking, this is the original implementation from the VAN paper. I think they did quite good work. Yeah, so it's not we specifically designed this, I have to say.
Got it. Yeah. Okay.
Okay, any other questions? Okay, then I guess we can stop with the presentation for now. And like I mentioned earlier, we're gonna go on a break for 10 minutes. So please be back in 10 minutes, and we're gonna go on with the other two teams. Thank you. Okay, I think we can start again. I hope everybody's back. So let's go on with the next two teams. The next team is gonna be, sorry, I forgot the university. Anyway, you know who you are, National Yu-Wen University, and the speaker is gonna be Yu-Wen Law. So I hope you are back. Please, are you there?
Yeah, and I want to share my screen.
Yes, please take this. So what do you say? You don't want to share your camera or what?
Yeah, I want to share my own screen. So,
Yes, please.
Okay. Thank you.
The screen is gone and we don't hear you.
Hello everyone, we are Yu-Wen and Ching-Hui from Team Brattoli Lab, and today we are going to present the method we use in the OCELOT competition. Our method is called Enhancing Cell Detection via FC-HARNET and Tissue Segmentation. This is our outline for today. We will introduce the method we use, the result of our experiments, and a summary of our report and future work. In the cell section, we change the task of cell detection to cell segmentation, which requires some pre-processing of the label. Our approach is to use the cell center coordinate provided by ground truth as the center of the circle. And draw a small circle with a radius of 5 pixels on the image to roughly cover the range of cells in the original image, and then of this precision as a mask for cell segmentation and input it into our model for learning. After training the model, we need to find out the cell location according to the outputting map of the model. The following is a diagram of a cell location. The brighter the space, the higher the value, the more likely it is the cell location. So we will take out the location maximum in this heat map, and if the peak value is also larger than the threshold we set, it will be judged as a cell location. Next, we explain how we use the result of tissue segmentation to assist cell detection. We build a two-branch network, including cell branch and tissue branch. We will take the cell coordinate predicted by the cell branch and map them to the tissue branch to find out whether the location belongs to a cancer-infected region, and then use the predicted classification result of the tissue branch as the final cell classification output. We construct this two-branch architecture so that the cell branch focuses on predicting the location of the cell, while the tissue branch has more information about the surrounding tissues in addition to the target region that we want to detect because of the larger scope of an image, which is suitable for assisting in the classification of the cell. This design can enhance the ability of the model to better understand the relationship between cells and tissues. In the tissue branch and cell branch, the segmentation model we use is FC-HARNET. FC-HARNET is a U-shaped encoder-decoder architecture in which the encoder and decoder part are composed of HARNET. FC-HARNET has been proved to be feasible in many semantic segmentation applications, such as self-driving car, traffic management, street image and medical image segmentation, and can achieve real-time speed, so we apply it to this cell and tissue segmentation task. When an image is inferenced, it will first be flipped horizontally and vertically, and then enter into the model to get two results, and finally average to be the output of a model. When we train 400 training images, we will do 5-fold cross-validation, so 5 submodels will be generated. When each image passes through a submodel, a test-time augmentation will be done, and one result will be output after average, and the 5 submodels will be averaged again for the final output. Next is the experiment result. We demonstrate performance improvements in cell detection through the following 3 steps. Initially, training a cell detection model solely based on cell labels results in a score of 0.686 on the validation set. Next, we decouple responsibilities with cells focusing on localization and tissues handling classification. This approach achieves a score of 0.7008 on the validation set. Lastly, we further enhance performance by utilizing a 5-fold cross-validation and a test-time augmentation in sample method, raising the score to 0.7182. On the testing set, our method achieved an average F1 score of 0.9693. This demonstrating improvements in cell detection by incorporating tissues information and improving in-sample techniques. Finally, we have the conclusion and future work. We use FC-HARNet as a training model and obtain good results in cell detection and tissue segmentation tasks, and also successfully utilize the relationship between cells and their neighboring tissues to improve the ability of cell classification. We hope our approach can contribute to progress and innovation in this field. Finally, for our future work, we have found that different types of cells may occur in neighboring tissue, and if they are classified in the way we propose, neighboring cells will be judged to be the same class, resulting in misclassification. Therefore, we should allow the cell to interact with the information of the tissues in the process of training, so that the model for detecting the cell will also have the ability to classify the cells, instead of relying on classification of tissue model only. Our presentation concludes here. Thank you for listening.
Thank you for your presentation. So do we have questions from the audience? We have a question. How did you ensemble the model predictions? For example, predicted the cell coordinates from different models will be slightly different. How do you ensemble them?
Actually, we ensemble the model output, 就是 ensemble heat map. So, and then average the heat map.
Okay, so simple average of the heat map output. Okay, any other questions?
Hello. Oh, hi.
Yep.
I have a quick question. Thank you very much, firstly, for the nice presentation. Oh, all good?
Yeah, all good.
Yeah. Okay. Yeah, I was just curious. On your main concept slide, you talk about revising the class. I'm just curious how this revision of the cell class, how it's done, like what kind of network is used there.
You mean a model architecture, right?
Yeah, is this final revision step just an assignment, or is there a learned component?
就只是单纯的在 tissue branch 那边嘛。但是为什么vision 是修的？
So I guess I was curious if you just similar to one of the previously presented works, if it's CA, then you set to TC, either that or it looks also a bit like a learnable network. We can also follow up offline.
Can you speak one more time because my network is delayed?
No worries, that happens. I was curious if the box that you show as final revision, if that is a neural network, or you are just deciding the cell class using the tissue branch prediction.
Yeah, I just decided a class by tissue segmentation output.
Okay, got it. Thank you.
Got it. Okay, thank you again to the speaker. Let's go to the last team, which is the team from University of Science and Technology of China. I'm not sure who the speaker is, so please just you can start talking.
Hello, can you hear me?
There you are. Yes. Could you share your screen? Good sign.
Can you see my screen?
Yes, only the desktop. Okay, now we see the presentation. Can you introduce yourself?
Okay. Hello everyone. This is a solution to MICCAI 2023 cell detection from the cell tissue interaction challenge by Team Saltfish and from the University of Science and Technology of China. This page is an overview of the competition, and as mentioned before, we won't go into detail here. And next, we will introduce our method. This page is the method of us, and it includes the pre-processing and data augmentation and post-processing. First, similar to OCELOT paper, we define the cell detection as a segmentation task. Specifically, the cell labels are provided as a segmentation map by drawing a fixed radius circle centered on each cell point annotation and filled with the corresponding class label as shown in Figure A and Figure B. And besides, we apply normalization to the image before they were fed into the network. And about the data augmentation, we first resize the image to a size of 512. Then we adopt data augmentation into flipping, rotation, Gaussian noise, and Gaussian smoothing during training. And as to the processing, at the inference time, we find local peaks within the predicted cell probability maps and output them as point predictions. In this page, we will introduce the large-scale pre-training model, segment anything model. The segment anything model is trained with over 1 billion masks and 11 million licensed and privacy respecting images, and mainly of them is about natural image. And we adopt the VIT image encoder of the pre-trained segment anything model as our encoder to enhance the feature extraction capability of the model. Specifically, we choose the VITH version of the pre-trained VIT image encoder, which has 632 meaning parameters. And however, we cannot directly apply the pre-trained SEM model to the existing cell detection task due to the significant differences between the natural image and the medical images. We adopt the LoRa, the low-rank adaptation of large language models. And this page, we will introduce what is LoRa and why we use it. An important paradigm of natural language processing consists of large-scale pre-training on general domain data and adaptation to particular tasks or domains. As we pre-train larger models and full fine-tuning, which retains all model parameters because less feasible. So, but we adopt LoRa and low-rank adaptation, which freezes the pre-trained model weights and injects the trainable rank decomposition matrix into each layer of the transformer architecture, greatly reducing the number of trainable parameters for downstream tasks. It is worth mentioning that there is no additional inference latency when we adopt LoRa. When deployed in production, we can explicitly add the original W parameters to the AB matrix parameters from the bypass to form the new W parameters, then proceed with the inference as usual. So there's no additional inference latency. This picture is our network architecture. As mentioned before, we adopt a VIT encoder of the largest scale pre-trained segment anything model as our encoder. Furthermore, we adopt the LoRa to fine-tune the pre-trained model VIT encoder, aiming to enhance its adaptation to our specific task. And we freeze all the parameters in the image encoder and design an trainable bypass to each of the transformer block and apply LoRa layer to the Q and V projection layers of each the transformer block in image encoder. To address the cell tissue sample path, we propose a dual branch architecture comprising separate networks based on a U-net-shaped decoder architecture for cell and tissue segmentation tasks. Notably, we replace the convolutional layers in the decoder with depth-wise separable convolutions to reduce the number of parameters and simultaneously enhance the model's generalization performance. And in the decoders of the tissue and cell branches, dropout is applied with the probabilities of 0.1 and 0.3 respectively. And for images with ground truth YT and YC, denoting the tissue label and cell label respectively, we use a summation of dice loss and cross-entropy loss to supervise the classification result of two branches. This page is about the experiment settings. So we can look, we can have an overview of our parameter settings. Okay, let's take to the next page. This page is about the results and the discussion. To analyze the effects of the proposed method, we sample 40 labeled images from the train set and use the other 360 to train our model. And we report the mean F1 score as a primary metric, which represents the average F1 score of all cell classes. All the networks are built with pre-trained SMVITH as a backbone, and we evaluate the effective of cross-entropy loss, dropout, and depth-wise separable convolution respectively. And in the final, we adopt model ensemble. We train 4 models with the same architecture but different initializations and respectively, and merge them together in the prediction stage. That's all. Thank you. Thank you for listening.
Thank you very much. Very interesting and simple approach. Let's get to the questions. I don't see anything in the chat. We have Seonwook. You raised your hand.
Yeah, hi. Thank you. This is Seonwook from Lunit. Thanks a lot for the very interesting presentation. I think it's a very cool idea to use SAM pre-trained weights and then LoRa for efficient fine-tuning, along with depth-wise separable convolutions in your decoder. I actually have many questions, but I want to start with the first one. So how did you pick your backbone or your pre-trained weight? So for instance, there's also the option of using Dino V2 or something trained with self-supervised learning. There is also the option of using something that is pathology specific. So there are several papers like C-TransPath that have pathology pre-trained weights. Lunit has one too. So I'm a little curious about your choice of the SAM VIT huge.
Well, first of all, the SEM model is a very powerful model trained with millions of pictures, and we have seen many methods use SEM encoder to as their backbones. So we also choose this as our backbone, and we do not compare other backbones. Maybe they can perform better.
Okay, all right. May I ask, like, how many trainable parameters did you have then in the end? This is just curiosity. Oh wait, can you hear me?
We can hear you.
Oh, okay. I don't need an exact number. I was just curious how much LoRa reduces the necessary trainable weight. Did we lose the speaker?
I guess you have to read the paper then.
Okay, happy to do that. Thank you.
Okay, so I see Lee is still online and is not muted, but we don't hear you. Okay, let's just move on to next section. So thank again Lee and all the speakers. Let me get the screen. Ah, there you are. No, okay. Let's move on. Do you see my screen? Okay, thank you. Yeah, so we heard from the top 5 teams, all very interesting approaches. So no matter the winner, I think we are all winners. Anyway, let's get to the fun part of today's event. Before showing the ranking, I wanted to give you a baseline, an idea of how a cell model without any tissue information would perform, and you can see this number here. And so on the 5th place, we have the team from Yu-Wen Law. So congratulations for your 7% boost on top of our baseline. I think that's a really good achievement. So a round of applause for Yu-Wen, please. Okay, you cannot hear me, but everybody's applauding. Then 4th place. 4th place, we have our friends from Bio-totem. They get a little boost, pretty good, and fortunately not enough to get to the top 3. But again, a round of applause for this important achievement. And finally, for the podium, on the 3rd place, we have Lydia, the team from Zurich, with a good 71.7% and their very simple approach. And to congratulate you on this third place. We have produced a certificate for you, which you will be able to download. We're going to send this by email, I guess. So, round of applause for Lydia. Really good placement. Finally, we have the last two. So who is it going to be? We have Joshua and our friend Lee. So next, I'm going to show the second place. Be careful, don't jump in happiness. This is going to be the second place. And I have here. Can you hear it? Boom. Joshua, congratulations. You are second place of the OCELOT challenge. Here is your certificate, nicely made by our friend Mohammed. He's the very good artist, decent scientist. And finally, a round of applause, please, for Joshua. I guess we did it. Finally, first place, we have Wang Kai, who wins this OCELOT challenge. And so to summarize the performances, we have a 72.2% by Joshua, a 72.4%, a very close one, by our first place. And I guess it's really like a simple model versus an ensemble model, and you can see there, pretty good challenge. So like Aaron explained at the beginning, you're gonna get your prize. Be aware this is tax deductible, and okay, the boring stuff. Lunit is gonna take care of tax information. We're gonna get your information, etc. And I guess that's it for the winner announcement. And so from the whole OCELOT team, we are very happy of your achievement, and we thank everybody for participating. Don't leave yet. Let's have some concluding remarks, unless anybody from Lunit wants to say something more about the winners and the winning. I don't want to put anybody on the spot, so.
Yeah. Just quickly, congratulations, everyone. Yeah. As Biagio said, we all learned today, and that's important for science. And congratulations to the winners. So thank you very much for participating and for following up on OCELOT. It was a nice session, and thank you for preparing for today. Again, a round of applause for everyone.
Thank you, guys. To conclude, we have some announcement. There's gonna be an on-site event organized by MICCAI, where OCELOT is gonna have a short 30 minutes presentation. On site will be Jae-woong and me, who are organizing, who are among the organizers. And we don't know the details yet. Please stay tuned on the MICCAI site and come and see us and talk to us if you're interested. If you do go to MICCAI, please send us a message and we can meet in person. So I will be there and Jae-woong will be there, and you can DM me on LinkedIn or write me an email. Then, directly related to the challenge, we have actually proceedings. So we have a collaborator who's gonna publish the articles. And who is invited? Well, the teams who submitted to the OCELOT test phase, including the 5 that talked today. The timeline is, paper submission is between the 6th of October and the 5th of November. So we have quite some time. Review and decision is going to be between the 6th of November and the 19th of November. And finally, the revision and camera ready are going to be, needs to be submitted between the 20th of November and 26th of November. Overall, the publication should be around 8 to 10 pages, so a real CVPR type of paper, including references with Springer format. You have a link here, and I guess we're going to give you more information about this if you don't already have them. Finally, I want to remind again, like Seonwook already introduced, that we do have a lot of open position. We are expanding a lot in Lunit, especially outside of Asia, but also in Asia. So please visit our website to know which positions are open. In particular, in the research field, I guess we are all more or less here from the same field. We are hiring on multiple candidates from each of the following. So we are looking for senior research scientists, which can be in the office in Seoul or globally from home. We're looking for senior research engineers, and we're looking for research scientists. So we have for everybody. So please contact us and look for us. Thank you again. If you have questions, you can submit your emails to oncologyairesearch@lunit.io. And that's all from us. So thank you for participating, and thank you for submitting and following the challenge. That's it.